Hi guys, in my last video my homebrew computer was being rather unstable and I said that it was frustrating to debug why. This time I'd like to get in a better position to debug what's wrong, and the main thing I'm going to do to enable that is add a very simple serial output port. So normally you'd implement this by adding an off-the-shelf UART, however for my purposes that goes against the grain a bit. I'm not trying to add full serial support to the system, I just want an extremely simple debug output interface. Using a UART would add complexity back into the output chain here, which I'm trying to avoid. Things like having to initialize the UART's registers to the right values on startup and things like that. So similarly, it's possible to use the 6522 for serial output that's already in the system, but again, I would prefer it if this debug output system didn't rely on correctly initializing the 6522. Luckily, the serial protocol is very simple, and it should be easy to output a byte of serial data with only a few ICs. So let's look briefly at the protocol first, and then I can show you the circuit that I've got in mind. I'm using TTL logic level serial rather than the RS-232 signal that typically goes down wires between computers. So with this system, the level on the transmit output line will either be 0 volts representing a clear bit, or 5 volts representing a set bit, and my diagrams here are drawn that way up. In this diagram then, I've shown two examples of bytes being sent, with time flowing from left to right like on an oscilloscope plot. Looking at the top example first, the transmit line is initially held high while no data is being sent, but then when we want to send some data we need to send a start bit, which is always a 0 bit, followed by the actual data. So we pull the transmit line low for 1 bit duration, sending the start bit, and then we send 8 data bits each in turn, starting with the least significant bit. After these 8 data bits we return the line to the high state for at least one more bit, which is the stop bit, and then after that we can either send another byte immediately if we have one ready to go, or if we don't have any more data to send, we just leave the transmit line high until we do need to send more data. The data byte being sent in the first example here is hex 55, which consists of alternating set and clear bits, making it very easy to see the bit boundaries in the signal. In the second example, however, I'm sending the byte hex F0, which has 4 set bits and 4 clear bits in a row. And in this case note that we still pull the line low for the start bit, but after the 1 bit duration of the start bit the signal stays low because the least significant data bit is also a 0. And then it stays low through the next 3 bits as well because they're also zeros, until it gets to data bit 4, which is set, and then it goes high, and now it stays high for the whole of the rest of the byte. When it reaches the stop bit it's already high, so there's still no change to the signal at that point, it just stays high for 1 more bit duration. This might all seem fairly obvious, but a consequence of it is that it's not really easy to see exactly where the bit boundaries are just from the signal itself. It relies on the sender and receiver agreeing on the frequency at which the bits are going to be sent, and that's called the baud rate. For my purposes, I'm going to use a baud rate of 112,500, which is fairly fast for a serial link, but should be quite stable. And the byte format I've shown here is known as 8N1, meaning 8 data bits, no parity bit, and 1 stop bit. So I'm going to need to configure the serial receiver at the other end with these parameters. Let's have a look at my little circuit then. This is the simplest thing I could come up with, and I think it'll do the trick. The inputs over on the left hand side are the CPU's clock, an active low chip select signal, and 8 bits of data from the CPU. So the interface here is quite similar to many other devices on the bus. The CPU's clock is far too fast to drive a serial connection, so the first thing I need to do is divide that down to the speed I need, and that's done using a 40103 down counter. I can configure whatever value I like by connecting its P0 to P7 inputs high or low, and it will then emit a low pulse on its TC output pin for 1 CPU clock cycle out of every N. To calculate values for N, I made a spreadsheet with a list of interesting baud rates. So in cell B2 I can configure a CPU clock frequency, and the numbers in columns C through E are typical frequencies I use in my circuits for reference, so I can just copy and paste them in. It then works out what the divisor needs to be for each of the chosen baud rates, and based on that divisor it quotes what the actual baud rate will be that's being output. As it's not going to be precisely what was asked for, it's going to be rounded to some multiple of the CPU clock frequency. The error percentage row shows how imprecise it ended up being in the end, and the 8N1 slew row calculates how out of sync the transmitter and receiver will be by the time it reaches the stop bit at the end of the byte. And I'm measuring this slew in bits, so in theory any value between -0.5 and 0.5 is probably fine, However, I'd like to keep it within a quarter of a bit's width of 0 if I can. As you can see, for the 115,200 baud rate that I'm targeting, using my current CPU clock speed of 4.5 MHz, the precision is actually very good. The last two lines in the spreadsheet refer to the time it takes to send an entire byte, first in microseconds and then in CPU cycles. So note that even at the relatively fast baud rate I'm using, it's going to take nearly 400 CPU cycles to send the whole byte. Serial communication is relatively slow compared to the CPU's bus speeds. Anyway, the main takeaway here is that we need to divide the 4.5 MHz clock by 39 to get 115,385 baud, which is close enough to 115,200. So here's an updated circuit diagram where I've configured the 40103 down counter appropriately here with the divisor set to 39. Pin 9 on the 40103 is an asynchronous parallel load signal, and I've connected that to the chip select input for this circuit. That means that when the CPU writes a byte to this circuit, the 40103 will immediately be reset and start counting down the first bit's duration, and that's going to be the start bit. It will send notches on the baud clock line at regular intervals after this point. Looking all the way to the right hand side of the circuit, you can see a 74HC166 shift register, and this is a parallel input serial output shift register, the same kind I use in my video circuits to output successive pixels between video RAM reads. It's being clocked by the baud clock line, of course, and its output forms the transmit line for the whole circuit. So whatever data we load into the shift register, this chip will output one bit of it at a time at the rate determined by the baud clock signal. As it shifts out the bits of our data byte, it will also shift in whatever we set on its DS pin, which is pin 1. And I've set this high so that after the last bit of data is sent, the transmit line will stay high, and this will form the stop bit. As we saw earlier, we also need to send a low start bit at the start of the transmission, and this is a little bit more tricky. I'm doing it here by clearing the shift register completely when the CPU performs its write operation via pin 9. This will make the shift register's output immediately go low, and that will be the start bit. The only thing that remains then is to load the actual data that the CPU wrote after exactly one baud cycle. The CPU won't be providing that data anymore because it will have moved on to do other things, so we need to remember what it was, and that's what U2 is doing in the middle here. It's an 8-bit D flip-flop register that I've used for this kind of purpose in a lot of different circuits. The final piece of the puzzle is making the shift register perform a load operation on the first baud clock pulse, but perform shift operations on the subsequent pulses. And in order to do that, I'm using an additional D flip-flop over here, that's a U3B, to provide a signal to the shift register's active low parallel enable pin. This flip-flop is cleared to 0 when the CPU write occurs, and it stays 0 until the first baud clock pulse, and that ensures that when that pulse hits the shift register, this 0 value causes it to load on that first pulse, but after that this flip-flop will have gone high, so subsequent pulses will just cause it to shift instead. So I have a good feeling about this circuit. It's fairly simple, and I think it's going to work well. So let's build it up and test it. So here's most of the circuit built on the breadboard. I did this off camera to speed things up a bit, but what we've got here is the 40103 down counter, which will divide the CPU clock coming in here to form the baud clock, and that's pre-programmed with the 39 value that I mentioned earlier on. So it's going to divide the CPU clock of 4.5 MHz by 39 and output, I think on the blue wire here, 115,200-ish frequency. And it'll just be very short pulses on that blue line once every baud period. So this chip here is the D flip-flop. We're not using the bottom half of it, only the top half, and that's again mostly being used to track at the start of the byte, so that we can control the load signal on the shift register. This is the shift register. It's taking all of its inputs from the D flip-flop, the 8-bit D flip-flop over here, and I think this pin here is the clock pin, and that's kind of chained through from the baud clock over there. The orange wire, I guess, is the parallel enable pin coming over here. I can't remember exactly which pin's which, but I think that's right. So that's coming from the output of the D flip-flop, and it's telling the shift register whether it should load or shift. And on the first clock it'll load, on the remaining clocks it needs to shift. And yeah, again, this is the 8-bit D flip-flop. I've hardwired a number here. What's that going to be? We've got this bit 6 is set and bit 0 is set. So that should be a capital A, I think. that we're kind of hardwiring in here as if the CPU had sent it. And the reason I've stopped at this point is because rather than hook it straight up to the CPU, I'd like to do some manual tests on it first to make sure that the circuit is generally doing what it needs to do. As I said before, this green wire here should be the CPU clock, and this green wire here is the output that should receive the serial signal on it. So in order to test this manually, I need to send a very short pulse to the chip select line, which I think is the red one here. It also acts as a reset line for the whole circuit to make it send a byte. So I need to send a very short pulse on there, ideally only one CPU clock cycle, and that's very short. I'm not going to be able to do that with my fingers. So what I'm going to have to do is hook up a button to start that pulse, and I'll probably just use an RC circuit at that point to make it just send a notch at the start of my button press. So in order to do that, I'm also going to need to debounce the button, because the bouncing effect of the button is going to be way longer than the duration of pulse I'm trying to send. So the first thing I need to do is low pass filter the button using an RC network to debounce it, and then I'll pass that through a Schmitt inverter, and after that I think I then want to just high pass filter it after that. And what will happen at that point is the filtered signal from the button, when the button is pressed, this second signal will spike up briefly to about 5 volts and then drop down again as the second capacitor charges. And then when the button is released, the opposite will happen. It will actually spike down to about -5 volts. Then to feed that into a digital circuit afterwards, I need to pass it through the Schmitt inverter another time to make sure none of these kind of intermediate values get sent to chips that don't know how to deal with them. So then the Schmitt inverter will output a nice clean 0 or 5 volt signal with fast transitions. And before it goes into the Schmitt inverter as well, I need to just protect the Schmitt inverter from those negative voltages when the button's released. So I'm going to add a diode here as well, just to clamp that to the ground level so that it can never go below ground. I'm not going to be too scientific with the component values here. I believe you can calculate it. It's just a regular sort of RC calculation for low pass and high pass filters. But what I'll do is just try using some components that I have to hand and see what happens with those. If it needs adjusting, then I might think about it a bit harder. So this here's a Schmitt inverter. So I'm just going to pop that in over here. I'll put it right on the right hand side, I guess, like so. That's going to need power and ground. Actually, maybe I won't put it quite so far over because it's a bit hard to get the ground wire in there. Let's move that back. Like that. We could put power. Then a button. Here's a button. I'm going to put the button over here, I guess. Oh, I've got an extra ground wire there already, that's handy. I'm going to use that. So that button is connected down to ground. As you saw in the circuit diagram I popped up just now, we need a capacitor across that button. What's this one? 301, that's 300 picofarads, I guess. So fairly small, but not too small. And then a resistor. The resistor goes to the positive rail, doesn't it? Tell you what I'll do. I'll bring it down to the positive rail from the inverter input instead. There we go. That should probably do. So this should be enough to debounce the button press. So what we should find is when we press the button, this capacitor will discharge fairly swiftly, and the input to the Schmitt inverter will very quickly go to ground, and then when the button is released it will charge up through this resistor, and it'll take a bit of time before that goes high again. If the button bounces, that will look like very short periods of being released just after it's been pressed, but the time delay on the RC network here should be long enough, or needs to be long enough, that the voltage doesn't rise enough in that period to trigger the inverter again. So if I see noise, then I'll just increase these component values until it goes away. Now the next stage of the circuit is a notch filter, and this is going to be taken from the output of the inverter here. And what we need to do is pass that through a capacitor. What's this one? 30 picofarads. Again, I'm not sure if that's going to be right, but we'll try it out and see. So I'm going to pass the output of that inverter stage through the capacitor into another inverter. So the capacitor is in series with the signal, and the resistor is going to take that to ground, so I'll do that like that. And like I said before, I need to also make sure it doesn't go below ground. So when the button's been pressed and then is released, it would normally send this to a negative voltage value, because the output of the inverter will drop suddenly, and the capacitor will take a while to charge back up to bring this to 0 volts. So in order to prevent that, I need a diode going from the ground rail to that signal line, which is just in parallel with that resistor there. And that means that when it does go negative, it'll just immediately discharge through the diode and come back to 0 again. So this chip won't see a negative input for very long. And then the output of that chip's where the magic happens. So we're going to grab that. What should I grab that with? It's a yellow wire. I'm going to take that output from that chip, from that second stage of the inverter, and that goes, I believe, to where this red wire is up here, and that's essentially our chip select line. So when we're connected to the CPU, this will be provided by a decoding circuit instead. But for the manual testing, that's how that's going to be wired. Just do it like that for now. Get it out of the way. So I can test that on the oscilloscope now. But before I do, I'm just going to wire up all the other stages on this inverter to make sure that they're not floating. So that should do the trick. So I'm not going to hook up to the CPU clock and so on yet. First I'm just going to power this, and I'll probably take signals from the button output and from the two inverter stages so that we can see on the oscilloscope what's going on with those signals, and just make sure that it's debouncing correctly and that the notch timing is good enough. And like I said before, the notch time I think needs to be somewhere between 50 and 200 nanoseconds. Anything in that range I think is going to be fine. If it's outside that range, I'll probably adjust it somehow by changing the resistor probably. So I'm going to connect my yellow scope probe to the button itself. I'll grab that from the input to the inverter. I always find these probes really clumsy to hook up. I can use the bottom of this diode as a ground. The blue scope probe can come from the output of that inverter. And finally, here's the red probe, and I'll take that from the output of the whole thing, which is where we're hoping to see a nice little notch. So there's the scope all powered on. Apologies about the noise if it's too strong. I hope you can hear my voice. We've only got one channel enabled there at the moment. Let's turn on the other two channels. And check the settings. Channel 3 is set to 10 volts. I want that 2 volts really. They'll probably all overlap each other. It looks like we're triggering on yellow here. Yeah, that's on the falling edge of yellow. So that actually makes sense because the button is going to pull this to ground. So that should get us the leading edge of the button press. Let's just have a look at what that looks like. Yep, so you can see the yellow line is coming from the button and that's gone down to ground. The blue line is the inverted form of that with debouncing, and that's gone up to 5 volts. So let's zoom in on that transition. There we go, they're all a bit more visible now, and you can see that there is a notch there, but the scope's run out of precision, so let's recapture at a higher sampling rate now. So you can see the yellow line goes down to ground here, the blue line has come up, it's ringing rather badly, but there's a small notch on the red line. How long is that notch? My time base is 200 nanoseconds per division, so I guess that's about 200 nanoseconds. So that's 100 nanosecond per division. Now I'm not sure if you can see the divisions, but that's about 100 nanoseconds. So that's what I wanted really, yeah. Interestingly, I'm not seeing much bouncing on the yellow line. I thought we'd have worse bouncing than that. So I'm just going to add a decoupling capacitor across the power rail just next to this chip to get rid of some of that ringing. Yeah, and as you can see, that's much better now. So the notch generating circuit seems pretty good now. So the next thing I want to do is hook up the clock to the 6502 computer so that that's driven at 4.5 megahertz, and get the oscilloscope connected to the output here and have a look at the serial signal coming out of that and make sure that that looks good for what we've programmed in. So I'm going to have to move it pretty close to the board here to get the clock to reach. So I can wire the CPU clock in like that. We need to link the power and ground, and we need to plug the actual power supply back into the 6502 computer circuit, because previously I just had it powered directly into the serial circuit. So now I'm going to hook up the oscilloscope's yellow probe to the CPU clock so we can just keep an eye on that. I'll hook the blue probe up to the board clock, so that's the output of that counter that I just hooked that one up to. And the red probe can just read the serial output here. So let's power that on and see what happens when I push the button. I think we're a little bit at the limits of what this scope can do when it's sampling 3 traces at once, because it's limited to 250 megasamples per second. So that's the yellow line is the CPU clock. The blue line is the board clock, and that's going down periodically. Now that will be going down at the rate of the CPU clock divided by 39. So let's switch the triggering from the yellow line to the blue line so we can get a better look at that. And I'll zoom out a bit as well and adjust the trigger threshold. So now we can see the blue pulse here lined up with the CPU clock. Let's zoom out a bit more and see when the next blue pulse arrives. There you go. So you can see a regular train of blue pulses, and these will be every 39 cycles of the yellow clock. In fact, down here we have the frequencies of the two clocks displayed, so we can see 4.5 megahertz. It jumps around a bit when the scope's at this precision, unfortunately, and 112,510 we have here, which is pretty close to the baud rate we were targeting. Now there's no activity on the red line, that's the transmit data line, but if I push the button we should see some activity on there. Before I do that I'm going to switch the trigger across to the red line because I want to get essentially a single shot capture of what's happening on the red line. Okay, well we can see that went low when I pushed the button and it came up again on the next board clock. In fact, that will have reset the board clock. We probably missed a board clock pulse there. I can't zoom out because the scope only captured that much. But what I'll do is zoom out and capture it again and we'll see what else happened. There we go. So you can see that there was a missing board clock here, and that's because we reset the board counter at the point that the CPU, or nominally the CPU, sent some data. But then you can see the red line went down for the start bit. When the blue line came along, the red line went up again, because the lowest order bit was a 1 in this byte that we're sending. Remember, we're sending the ASCII code for capital A, which is 65. So bit 0 was set. It then went low again for the next sort of 4 or 5 bits or so, or something like that. Then it went high again for bit 6, which was the 64 value, and so that 64 plus 1 is 65, which is the ASCII code for A. Bit 7 was 0, and then it went high at the end for the stop bit. And then as I showed in the diagrams earlier, it just stays high all the time after that when it's idle. Let's get a few more captures of that and make sure it's consistent. That looks good. Now I can also change the value that's being set up here, so maybe I should change it to send a B instead of an A. Actually no, maybe I'll make it send a C. So when we send a C, we're going to be setting bit 2 as well as bit 1, so we expect it just to stay high for 2 bits here and then go low, and the rest of it should stay the same. So I've changed the circuit. Let's reset the scope and try again. And yeah, that looks perfect. We've got a double length pulse at the start. That's bit 0 being 1, bit 1 is 1, these bits are all zeros, then bit 6 is a 1. So that total value there is 64 plus 3 is 67, and that'll be the ASCII code for C. So that all looks good to me. The next thing I'm going to do is hook it up to a serial receiver and see what we get. So this is the serial receiver I'm going to be using. It's actually a TTL VGA terminal from Debug Innovations. I'll put the link in the video description for the circuit diagrams and parts lists and things like that for that. It's a really nice design. The idea is it hooks up to your computer through a serial interface, and it outputs a VGA monitor signal. So you get a bidirectional serial interface. You can plug a keyboard in as well to send input to your computer. And at a basic level it just outputs it on the screen. It has some more advanced stuff as well for some graphics too. So it has the standard serial connector on it, but it also has a kind of set of pins here for TTL level serial instead of RS232. So this is what I'm going to be using today. So I need to hook up the the receive pin, which I believe is the 4th one along. And I'm going to need power, which I think is the 2nd one. And ground. And what I'm going to do is I'm going to power the board here, but then feed the power from the board to the computer. So I put it in this box to make sure it doesn't short on anything. Here's the monitor cable. It can go like that. And well, that's not really going to reach to the transmit line there. I'm going to plug it in here. Bit of a stretch. Plug that through. Then connect the ground and the power. Oop. Yeah, it's a bit of a stretch. So that's now all powered up. Let's see what's happening on the monitor. So you can see when we power it on, it has a little splash screen, it shows up there. And then we just get the cursor. So in theory now, anytime the computer sends any serial data to this board, it should appear on the screen. So I'm just going to push the button and trigger it to send that character, which I think I set it to a C in the end, didn't I? Let's see what happens. Yeah, that looks correct. We have a C at the top of the screen. Every time I push the button, it sends a letter C. And I can change it to send something else instead. What have I done there? I've set that to it's probably a G now, I think. Yep, that's a G. And I guess this is going to be an O. Perfect. So this shows that the value I'm configuring on the inputs to the 8-bit D flip-flop here are controlling which characters get displayed on the screen. So when I hook that up to the CPU's data bus and hook up the notch signal to some form of address decoding, this should allow the CPU to send any data it wants just by writing one memory address, and it'll appear on the screen. I won't do that right now though. I think that's enough for today. So in the next video I guess I'm going to implement some address decoding to generate that pulse signal and hook it up to the CPU, rewrite some of the I/O routines in the code, and see if we can use it to output basic debug information from the system. And then maybe we can diagnose what's going on with it. So since I started making this video, none other than Ben Eater has produced his own video on the serial protocol. He was focusing more around receiving it so far, so it'll be interesting to see where he goes next with that, but do check it out. He's got a really good way of explaining these things, and it might complement this really well. And if you're interested in a much deeper dive into all of this, making your own serial UARTs and things like that, James Sharman's done a fantastic video series on that. I'm not going to go anywhere near that far with this. I just want a basic debug port here. But yeah, for a deeper dive into that with a much better implementation of everything, do check out his series. Thanks for watching and have a great day.